In this video, we deepen our understanding of the motion of gas particles by taking a look at how kinetic theory of gases explains the average kinetic energy of a gas. Right, in a prior video, we actually have carried out a full derivation for how you can understand pressure from a kinetic molecular perspective. And what we actually have obtained is that the pressure in kinetic theory of gases has this expression. Okay, the pressure of a gas is directly proportional to the number of gas molecules or particles that you have over the volume of the container of those gas particles, multiplied by the average kinetic energy of the particles. Now, we're going to talk here a little bit more about what this kinetic energy means. Okay, well, we already know what the expression is, or one of the expressions for kinetic energy, which is simply 1/2 the mass of the gas particle times the average of the velocity squared. Okay, but we're actually going to learn how this kinetic energy is also related to temperature. Okay, this is the expression for pressure in kinetic theory of gases, but this pressure should be exactly the same as the pressure that we can calculate from the phenomenological ideal gas equation of state. Alright, so what we're actually going to do is solve the ideal gas equation for the pressure, and then we will be able to equate those two. nRT over volume, okay? And again, we now have two expressions for the pressure, which should be exactly identical to each other, okay? And that is going to allow us to see what the relationship between kinetic energy and temperature is. All right, let's proceed. We have 2/3 of the number of molecules or particles over volume multiplied by the average kinetic energy, and this is equal to the number of moles, RT, over volume. Okay, so right from the get-go, we actually find that, well, we can get rid of the volume because it cancels out from both sides of the expression. Now, what we actually have here is the number of particles and the number of moles, but it turns out that those two things are related. Right? Notice that the number of moles, okay, is equal to the number of particles that you have divided over Avogadro number. Okay? All right, so then we actually can replace this by the number of particles over Avogadro's number, which is the number of particles in a mole. So that gives you the total number of moles that you have. And then you find that you now can also simplify or cancel this number of particles. Well, great. Let's then come up with the next step, which is kinetic energy. Let's solve for it. This is going to be equal to 3/2 the gas constant over Avogadro's number multiplied by the temperature. Okay? Alright, so it turns out that these are two constants. That is the gas constant, and this is Avogadro's number, so the ratio is going to be a new constant that we're going to be called Boltzmann Constant, case B. And this Boltzmann Constant has a value of 1.381 10 to the minus 23 joules per Kelvin. Okay? Alright, so we have finally an expression for the kinetic energy, which is this, which is very useful because it allows you to express how the kinetic energy depends on the temperature. It's equal to 3/2 K sub B constant times the temperature. Alright, so let's see if we can understand that expression a little bit more. This expression is very, very thought-provoking, okay, because it tells you that the average kinetic energy of a gas does not depend on the nature of the gas. It actually depends only on the temperature at which the gas is. And again, that is very thought-provoking. Let's think about two different gases like helium and oxygen. Obviously, helium is much lighter than oxygen. When you look at the periodic table, the atomic mass of, or the molar, the atomic mass of helium is 4 AMUs, but the molecular mass of oxygen is about 32 AMUs. Right, so clearly oxygen is more massive than helium. It's actually 8 times heavier than helium. However, when you actually think about these two gases or a collection of these two gases at the same temperature, say 300 Kelvin, the average kinetic energy should actually be the same, or is the same for both gases. Okay, so let's see if we can actually reconcile that. Again, we have two expressions for the kinetic energy. That tells us that if the temperature is the same for both gases, then the kinetic energy should be the same. So the way to reconcile that is to come to this expression and say the following. Look, this mass is actually going to be very different for two different gases, helium and oxygen. Right? In order for these to be the same for both gases, then the velocity has to also be different. Right? So what we will have is that even though helium is lighter than oxygen, right, the average velocity should be much larger than oxygen, so that the kinetic energy is the same for both. Okay? And that actually makes perfect sense, right? So at a particular temperature, something that is lighter is going to be moving on average faster than something that is heavier, which on average will move a little bit more sluggishly. Okay? So that is our explanation for kinetic energy and how it depends on temperature. Okay? In the next video, we're actually going to find a useful expression to calculate what the average velocity of a given gas is.